Welcome to the controller section of the robotics course. As we dig a little bit deeper, we've gone through the introduction to the basics of robotics, giving you an idea of the breadth of the actual field, the different areas that would actually be involved and that you can branch out into. We then went deeper down into the basics of electronics, going through, current and voltage and amps and cycles, and now we're going to step back and now look at controllers. Key part of what we'll be working with this course, and the thing we have to start with, because everything else will be connecting back to these devices, and they'll be doing our work with. So, I'll shrink myself down, and we will get going. So to remember that we have to, in this course, remember this general cycle that I've been talking about, or this closed loop control that I'm referring to as the robot control loop of sensing from the environment, taking that sensor and thinking about the information, doing some action with it, and then sending information out as well, and continuously going through this cycle and being careful of how much time is spent in each. That's usually like sense, think, act, sense, think, act, sense, think, act, and looping through all those components. Now, in the robot control loop, remember that the think state, again, was where things like task planning, classification, learning, processing of signals and data coming in, path finding, motion finding, or just simple things of based upon this sensor, this is what happens. Or if we have no sense information, just direct, okay, this is the action that should be going on. So really, this is the kind of state in the actual robot that's taking the information, doing some kind of actions. And as you expect, and it's been mentioned before, controllers. This is where that work happens, that your sensors, effectors, actuators, and power are all connected to the controllers or provided by them, depending upon what you're working with. But in that key part of it, this is where you're adding in your programmable part in the software aspect of that controller and the thinking part of whatever your robot is. And so before going on, we need to understand in general, well, what are controllers, what different types are out there, and get a basic feel for it, because again, they branch out far. That wherever you go in the future, there'll be new ones next year, new ones next month, whatever is actually being developed, or modifications, new technology, but the same general ideas there of what are these controllers? And you'll also have to decide upon it, because if you're working on a project, you need to decide upon what are the proper sensors, effectors, actuators, what's the proper power source, and what's the proper controller for what you are working on. So our handy-dandy little humanoid robot we had before, and remember that controllers basically kind of act as the brain, the brain of the robot. There's more to it, and there's multiple things that can be linked together, but this is the idea. If we're trying to break down what is the hardware software that is making decisions and thinking, well, it's going to be the controllers and how they're combined together. So it's the hardware that contributes to processing of sensor information and triggering of actions. And that hardware itself then could have a stored program or program built into it. And it involves mechanical aspects and that programming part that we are working on. So it's going to be highly important that it may provide ways that you have power connected to it for source and management, connecting to other controllers, doing all that kind of information. So it's the first thing to start with, and then everything else you're connecting on to that afterwards. So it's usually a computer of some sort, and that can be a loose definition of this from a standard computer like you're watching this video on, or I'm recording this on, or something very more simplistic, depending upon what the project is, that has less features than what you're used to for a general purpose computer. So computer of some type, which stores information about the robot and its working environment and executes programs which operate that robot. And so that's, again, a loose definition. So we need to have some kind of area where we're saving memory. That we have access to that. So memory being your variables, whatever else, storing stuff from sensors that the robot gets as it goes and has a place to store it while it's doing its work. There's pre-programs, so those lists of instructions that the robot should be actually following that you guys will be doing. You're on that side of that kind of development and operating the rest of those. And the control system contains programs, data algorithms, logical analysis, various processing activities. Like, it depends upon the level, like from larger to smaller. But whatever algorithms you have to do with the analysis of that information. Like, we're going to be starting with very simple stuff in this class, but you could build up to a lot more complex. But it also is limited by, well, what's the type of controller you're working with? It's not just the same machine that you're working on now in some cases, especially for this course, or is it more complex where you do have that access to it? Depends. It's your project and the equipment and the physical realities of stuff that you're working with. So more sophisticated robots may have more sophisticated control systems. As I was just saying, like, we're going to start very simple. It's the beginning point, but you can get more and more complex. If you look at anything that Boston Dynamics has created, like, and NASA, like, these are much more complex. Beyond just having one controller thinking about this as one brain, we may also have multiple different controllers that work and coordinate together. So you may have like one main board that's doing something, but you'll have other specialty boards that are then connected to, and each one of those boards has its own task and programs of what it can actually controls. So the main board may send out a signal and tell it what to do. It's like motors. Maybe you have a separate motor controller, and you have a main board that communicates it telling you, okay, well, turn motor 1 on to this speed. And then the motor controller receives that signal and then knows what power and what messages need to be sent to the actual motor signals to achieve that desired requirement. And we'll try to cover some of these later in the actual course. Maybe you have a more complex robot that is humanoid, and you have things like arms and limbs, and it's kind of a lot to have to force one controller to control every aspect of it. So maybe a robotic arm is built up of a bunch of motors and other things and sensors, but then there's a controlling board for that arm or for just that component of the arm, like the hand. And then the main controller then sends information to it. So these are important things to take into account. Now, for example, the Mars rover, Sojourner rover, was made of 2 electronics boards that were interconnected to each other with like a flex cables. You can see it here to the left. Right there, that you have 2 different boards. You have electronics. Basic sense, you may not know what everything's doing, but you know there's going to be conductive materials. You know there's going to be insulators. You know that you're going to have electrons moving. You have amps and currents. You have this flex cable that's connecting between the 2, which would have some kind of conductive material, and the outside of it, once again, is an insulator, and allows the communication between these 2. Like these thick cables, there's a whole bunch of little individual wires or lines that then allow for the transmission of signals of on, off, power, no power, and having that communication. And this is needed when it comes to specific requirements that are broken down for the overall robot that you're working with. So in this case, one board is called the CPU, so the central processing unit that's executing everything for the robot. And the other is the power board, and each contain items responsible for power generation, power conditioning, power distribution control, analog and digital sensor information stuff coming in, control and processing computing for the CPU, and data storage, i.e. memory of what's going on. So you can see that, well, more complex will have more things added to it, and you could take simpler, smaller controllers and connect them together and construct something more complex after that point. Especially nowadays, you can get that a lot more with the IoT or the Internet of Things kind of devices, the idea of having interconnected homes. Like everything we're seeing with the Google and Alexa and Siri and all of that of, well, okay, well, how can I start making devices and connecting them and having all these wireless or short-range Bluetooth or RFID or whatever kind of requirements that are allowing for these communication and distributing what you're doing with the actual devices or considering what you would consider to be the actual robot itself. Now, controllers, there's like, it could be a whole course on its own. Like every lecture I do for this could be its entire course, but this is just a beginning intro to give you that feel. And we'll be playing around with these more, but like there are a wide range of controllers out there, both industrial, commercial, and DIY or do-it-yourself. Like we're going to be sticking with do-it-yourself ones that are accessible, and as that market has opened up, because there's specialized one for industrial robots, other commercial uses of what you're working with it, and that get larger. There's fidgets and other devices that are out there, and new companies all the time, especially with the growth of automation and AI and access to robotic devices as it comes now and what will be in the future even a year from now. And then even the do-it-yourself at home, that like why we can have these easy access kits that are not that expensive, where give it 10, 15, 20 years ago would have been way more expensive and not in the realm for in-the-house kind of computation work. And even though it says do it yourself, like even though they're small controllers, you can do a lot with these and even get more specialized. So we're going to be concentrating in this class on Arduino, and I'll be explaining that at the end of this lecture. Like, why is Arduino? Like, what is Arduino? Why did I pick this? And why do, like, I personally think this is a good starting point in the course itself. Now, controller. So when you're designing a project, there's lots of things I've said you have to take into account already, like what sensors, what's quality of those actual sensors, what can you afford in general, and what will work for a project. And so controllers also play a role in this, of like, depending upon the design of your project, what controller should you use? So you need to decide upon the proper controller or group of controllers to use, and take into account what specialized controllers will we need on top of that. So motors or lights, and I'll go into this in more detail a little bit later. What limitations or restrictions or advantages and disadvantages and so forth do they provide? This isn't just like any program you're writing stuff. You have limitations. This is a physical device. You may only have a physical number of connectors, what power it can provide, what type of sensors can be actually connected to it, your case of if it's cheaper, how much do you trust it, because sometimes there's payoff reasons why it's cheaper versus more expensive, and is it worth it? Do we go for a $10,000 controller to control something that fades a light up and down? Probably not. Like you have to decide upon these. Also things, what community support is around them. This is something that I personally think is really big, is that you may see the new hotshot new device that's out there, but what if that company tanks and there's no support? How does this connect to sensors? What if it's only their sensors they provided? How are you going to fix this? How are you going to build upon the project? What access do you have for other resources that are out there? What open community do they provide for interchange between devices, between companies, even if they do disappear? And like, what future support are you going to get if you're building this device? And how are you going to maintain things? Fun. So for a main controller board, you'll generally find the following. Like, it's going to vary from there, but you need to take into account, okay, the specific programming language and development environment and compiler that it provides. Some, it's like you must use their tools and only their tools. They have a specialized language and a compiler that converts that language that you're writing into what the actual controller board itself will actually understand and deal with the transferring of it. Sometimes there's different compilers that allow for a multiple range of actual devices, but you need to take that into account. Coming into this course, I know some people have a wide range of background in that Java, C++ to Python, and so you're not taking into account, well, this is a new language that may look similar to what you've seen, but you have to make sure, what's the syntax? What's the semantics? What's the same and its difference? And you can't just type something randomly, and you have to make sure, does it fit for that language itself? And we're going to see that with the Arduino. It's going to be something that's similar to Java, and that people should be okay, but people who are coming with Python experience and not much other language experience, well, there's a difference, and you've got to learn, okay, well, how do I type these different? How do I make sure that the compiler computer and the machine are understanding these things properly? And I will go through a lot of examples as we build up in the simulator and the physical videos, and you should practice them yourself as well and look up other tutorials to start practicing with the language, understand what's different from the language you've been using for a while. Beyond that, it's also memory and storage. So what memory does it have for storing your programs? When the program's running, how much memory is it that it can actually use to store information as it goes? Because some devices, it's going to be very limited. You can't just be like, I'll make a program as big as possible as I want, or I will use as much memory, like make as big of an array as I possibly want. Well, maybe you don't have that, because with some of the smaller controllers and more simple ones we're working with, it's not the same as your general desktop computer. It has a limitation on how much memory. And a lot smaller in cases than you would probably think, especially for basic controllers versus microprocessors, which we'll be going through both of them again later in the video. So you'd be like, well, what memory do we need? What storage does it provide and everything else? What kind of processor is it? So processor being what executes the actual instructions in your program. Is it a CPU, so your central processing unit like a desktop computer? Or is it a specialized chip that's set up that has its own kind of specialized processor and the execution of the actual instructions? You need to take that into account, and we will be covering that in this video. Now, for the main controller board, you will also find things like power control. So that, in basic sense, is that the boards will have stuff built in so that you can plug some kind of power source into the controller itself, and then it provides ways to for you to connect to that power source. So we've seen this in the previous kind of lectures with electronics, that you can have like a battery, and you've got your anode and cathode, so you're positive and you're negative. You're positive and ground, all those different terms for the same thing, and we need to build our circuit to get anything done, or multiple circuits that are connected together. And the controller boards will allow for this. So, like when you're dealing with the controller board, you're not like, we'll have circuits, we'll have probably multiple different circuits that are connected to the one actual controller board, and it'll provide that power. But it has its own limitations, the same as that water cycle thing that we have, what volts it provides and what amps it actually provides. So what's its potential storage and what's the power amount that it can actually run. Because you may end up realizing that, well, okay, the board provides a certain amount of power and that's good for certain things, but maybe I need to add an extra power source that's connected differently to run something like motors or something that's more complex that maybe those motor controllers could deal with. But you will see them on there in the basic boards as power. You'll have some way to connect sensors and actuators and effectors. It may be the basic way. It doesn't mean you can just suddenly plug anything and everything together in. For special sensors and actuators and effectors, maybe you need to learn, well, how do I connect it? Maybe there's specific ways it needs to actually be connected when it's this controller, or maybe it's just not compatible at all, and you need to take that into account. Because you may have an idea, but before you go further into the idea and building, you should make sure, is it actually feasible? Can you actually do that? Do you know how to actually work with that? So what special computer libraries will you need for your programs? What special power sources? How many things can you physically connect together? Because again, it's a physical device, and they'll have ways to connect sensors and devices, but sometimes you're limited by how many things you can actually connect. I may not be able to connect and manage an infinite number of sensors on a very basic controller. There'll also be ways to potentially connect to other types of controllers. So maybe through common pins. We'll talk about this. Maybe it's networking that's built in other ways. Depends upon the actual controller. And you'll have different ways then that you can communicate and send information between those different devices. Basically like one controller and the program running on it giving feedback and being input to another controller and vice versa. These things are communicating. Just kind of like two people working together and talking to each other and getting the work done. And you have to set up that proper way to allow for them to communicate in the beginning. So, looking into these controllers, you need to look into all of this. I should probably take a break. I talk like fast all the time, so I learn like maybe I'll take a sip of water and slow the heck down. And maybe for some reason I take the rest of the video to get like some kind of southern drawl going as we talk about different kind of controllers, at least as far as this course is concerned. And I am not going to go with the rest of that voice because I'm just going to keep getting more and more horrible. So I'll go back to my normal voice. The showcase teacher voice. You've come to controllers, and you've got 3 doors to choose from. So as far as it is for this course, I'd like to have like breakdowns. So at least you have a starting point and some terminology to be able to talk about stuff, and going from the general idea of a controller and breaking it down into all physical different types and classifications of controllers. So for this course, I've created 3. So being either a microcontroller, microprocessor, or specialized. And we will start with specialized. And so specialized, or in this case, how I'm classifying it, these are more the boards that you will connect to a main board controller. And they provide features and things that your main board doesn't do yet, or you don't want to set up some kind of complex circuitry to deal with it, is that they provide one board and easy connections and other ways to deal with issues for you, and then you just need to connect them to your main controller and then connect whatever sensors or other things that are required to it, or whatever built-in sensors it has and so forth, and let them do their work. So examples of these could be things like there's one here to the left that shows you that you've got ways to connect little LEDs, lights, and all that fun connectors. And I think this one may be for a motor. I don't remember. It's a random picture for this one. I have more specific ones on the next slides. But you have things that could be controlling a whole sequence of lights. That could be maybe difficult. Like, we can start very basically on a board, deal with one light, but what if it's a whole string of lights? What if it's a whole billboard of lights? And maybe that could be a lot for one little board to do it if it's managing a whole bunch of other work. When instead we could have a light controller board that then has pre-built in tasks and ways to deal with stuff, and our main board just communicates to it. And that light board handles the power for all of those lights and keeping it separated from the main board. So we'll connect all of these, and maybe there's different ones you need to deal with. And so you should just be aware of these, is that when you're working on a project, well, what boards can I get? Is it able to connect to the controller I am working with? And what advantages or disadvantages does it also provide for you in placement and everything else? So example, I've mentioned a couple times, and may deal with it in this course. The kits and everything else that we have here, the basic ones don't have these. At the school has more. But you have motor controllers. So motor controller is a device that acts as an intermediary between your robot's main controller, batteries, and motors. So your main controller could have its own power source. Motors take a lot of actual energy or other power sources from this. So you generally have a separate power source when it comes to running your motors. And so these motor controllers will deal with being able to hook up what motors and things you're working with, hooking up the actual other batteries. So you can see the example here is that we have 2 other motors themselves here. You have a power source, what you're providing that's coming in. You have here the actual motor controller itself, and then you have these connection lines that are going into the actual whatever controller you're working with. In this case, it's an Arduino, which is a microcontroller, and you have a little joystick here as like an input kind of sensor. Let me go back. So this is an example, we'll go into this more, but the idea is that, well, that board handles stuff for you. And so it has its own requirements of how you connect the wires, what code you need to have on your actual controller itself, but it adds these extra special things on top for whatever project you're working with. So the more complex your project gets, maybe you'll have other boards, you'll search out there for what's provided, find companies that you trust that are developing stuff, and see what do they provide for you so you do not have to build everything from scratch. Which, trust me, there's things that you don't want to. Unless you're getting into the point that you need something really specialized for the project that you're actually doing, and you just design your own board, and that's a whole different market that's out there, and nowadays you have that ability. Design your circuits. I know there's online companies for doing printing of your circuit boards for you, so you don't even have to do it at home, and they can do small batch specialized ones. It doesn't have to be industrial grade, large scale kind of stuff. It's whatever designing you actually go through. Boom. Other ones you've probably seen this all if it's Christmas, is like light controllers and everyone having everything hooked up, is, well, again, they're special devices to be able to hook up streams of lights and then have different ways to actually control them themselves, and these are separate light boards. Other examples is, what if your controller itself doesn't have other networking or wireless kind of communication capabilities? Some controllers may have that built in, so hey, that's an ability, I will use that. Some don't. And you'll decide, okay, well then I have an external controller board that handles that for me. So the example one here of an Arduino microcontroller, so the bigger device, being hooked up to a smaller board here for doing Bluetooth communication in one case. And so again, all these specialized things and making sure they work and how you connect it up. There's probably even quick things you should be able to pick up from here, because you can see things like, oh wait, hey look, they got a red line and a black line, and that doesn't always indicate that you're like, hey, that's power. But hey, look, it's connected to something that's 5 volt. There's a good chance this is providing power. There's a good chance the black line is ground being negative. And then you have other wires to connect up for other reasons to the boards that we'll get into. So this is the fun. So these are specialized boards. There's a wide range of them out here, but remember, just think of them more as the specialty smaller controllers that do extra tasks for you and connecting together. And then you have these connected to your main controllers or other controllers, and then those controllers could be connected to other controllers. Again, depends upon the complexity of your project. So the other classification, we said that there was 3 of microcontrollers, microprocessors, and specialized. So just finished off in specialized, and so now we're getting to what are microcontrollers themselves, like as a term. And a microcontroller is a computer presented in like a single chip, which is different. This is not like for people who've broken down a computer or know anything of the basics of it, where you hear where there's a lot more to it. This is where no, everything is on one integrated circuit, one little chip, as you call it right here, the basis of everything that's important for electronics nowadays, of what's shrunk in there, insulating material on the outside, everything that's miniaturized on the inside of it, and then these connector conductive pins that all have their own specific meaning. But what you get these microcontrollers are these chips that have stuff stored on them. They have a processor, they have memory, and all of the storage and everything you need, and any program that's stored on it in here. And that's that key thing that you then connect up to other things, so connecting other devices and everything to them, like your sensors and everything else or whatever you're working with. So it's all integrated into one thing. It performs one task, and one specific application has no operating system. And this is important. Like when I say operating system, this means like, hey, like Windows or Linux or Mac OS, whatever, working with, and that manages you, that you have this graphical interface, you have these windows that can open up, you have all these multiple programs that are handling things behind the scenes, you can have multiple programs running at the same time. And with basic microcontrollers like this, none of that. You have one program. That's it. So whatever program has been loaded onto that actual chip, when it's provided with power, that program will start executing and will keep executing until something cuts power or something tells it to shut down itself. And that's it. Nothing else running from here, nothing of multitasking, just unless it's a specialized chip for something, but you have this basic one of one program, run it. Power on, run. Power off, stop running. That's it. Nothing else running from there. It also contains memory for your programmable input and peripherals and your processor, so all the rest of it. So some place to store the program itself, some place that the program can save information to, so kind of like saving to a file. Like this is a very big abstract in this case, but some area of memory that can be saved, so when it shuts down, it still has some information that's saved. And when the program's running, it also needs memory or space that it can do its work. So like when you create variables, those variables need to be saved somewhere. And so that's saved into running memory that you have there. But when the power's lost or the program shuts down, all that kind of information is gone. And so you have limitations of that. But it's all, again, on this one little chip. And so microcontrollers are mostly designed for embedded applications and are heavily used in automatically controlled electronic devices such as cell phones, cameras, microwave ovens, washing machines, etc. So when this comes to things like cell phones, this doesn't mean like what's running the actual OS on a smartphone. This means for smaller features that are built in, and then those microcontrollers are connected to more would be a microprocessor, and they're all working together to do some kind of task. But even more basic ones, it becomes smaller. So these are very rudimentary. They don't have a lot of very fast computational power, but they are the workhorses for your motors or your sensors and doing things very fast and collecting that information so that you can connect a whole bunch of different sensors, effectors, and actuators and have it handle it really fast and processing that information, but in the trade-off that you're not dealing with multiple more complex tasks like what would be involved in something a larger AI or something else and that's when we get to microprocessors would deal with that more. And like we're going to get used to microcontrollers in this course because that's the main one that we're going to stick with. Now, a quick example, because again, microcontroller is just one category and there's tons of different types of microcontrollers that are actually out there, and that is the Arduino Uno. which is just one device, and I'll talk about that later on. And it's the one that we're using in this course. And the biggest thing to see from all this is that this is an entire board, again, conductive, non-conductive materials, points where you can add stuff. But really what's important is there's lots of extra things that it actually provides. But this little chip that you see here, and there's a variation, I think the boards we're using this year, but really this is the microcontroller, this chip that you're actually seeing here. And the rest of these are just extra peripherals that allow it to do the rest of its work for managing power, connecting things, adding extra stuff that's in there. Another bigger thing you see example when it comes to things like these microcontrollers is it's very limited for other things. This is, again, not like your general purpose computer where you're going to be hooking up monitors and other devices and things like that. No, like you are working like with basic stuff or giving these input sensors. So you get things like what would be something connecting to the USB for loading a program or for power, other things for power, other things for peripherals and sensors they'll be going through. So much more basic in a way then that you can connect to other things. So it's rudimentary beginning. And rudimentary here doesn't mean bad. This is still good. It's a specialized task and a starting point for what you work with and for a lot of projects. And maybe it's not the fit if you need something more for AI, but if your AI has any kind of robotics and controllers, you'll be dealing with microcontrollers at some point in time anyways. Now, that last family of controllers are being microprocessors. As in this case, microprocessors are then basically like your desktop computer. Could be a whole computer, but that's way too large. But in general, this is some more smaller device that provides a similar environment to what you would expect to see from a desktop computer or your laptop or so forth. So it incorporates functions from computer central processing unit, so CPU. It has a single integrated chip, general purpose memory, runs multiple tasks, has an operating system, maybe one you're used to like Linux, maybe a version of Windows in some cases from this, or it's got its own special kind of operating system that deals with everything and doing that work for you. So it's much more powerful, like in the sense of how much information it can process and different tasks, so more complex tasks like analyzing images or doing other work, if you don't have some kind of external controller board that does that work for you. It'll allow you, in the case compared to desktop computers, these microprocessors that are used as a family of controllers will still provide ways to give power to other devices and will provide you with ways to connect up sensors that from your general desktop computer you won't get. If it's just built into it's a gaming laptop, whatever machine you're working with, that these other ones will give ways that you can connect things to them. Now, example that a lot of people maybe in this class have heard of or the thing here is different variations of Raspberry Pis. They are a type of microprocessor. And you can already see, like, they may look like a small board, but they've already provide some things that are completely different than a microcontroller. Like, I think this chip here is generally the processor. You have other memory, but you have connectors here that are HDMI for monitors. You have you have 3.5 millimeter jacks for like headphones or other sound. You have this like larger one here is for hooking up a network cable. You have plugins for USB connected, so you can plug in USB devices like other mice or dongles or those kinds of things. You have specialized cases like right here, these two slots here for the Raspberry Pi that allow to connect with like thinner ribbon cables. Being again, it's just bendable plastic that has like bendable metal and wires that are connected in it, that you can hook up cameras and other peripheral devices that are designed differently, like for the Raspberry Pi. And you also get these pins and stuff back here that we'll talk about a little bit later on, which is a way that you can connect other sensors and effectors and actuators and so forth from there. You have that ability. So, but with these, the idea is like, well, the controllers, you're loading one program on and that's all that it runs. And usually you need your own computer, you connect the controller to it, you can then download and get the actual computer onto that controller. Then that controller just goes off, you disconnect it and it just keeps running that one program you have from there on. Whereas with these is that you can remotely load programs onto if you want, but generally like you could also then just hook it up to a monitor and do your work on it, convert everything and do that work with it. Depends. So you can remotely control it. You can hook up your monitors and program it and disconnect those and do whatever else. Depends how you have things set up and what you're actually doing. It's all depending on the actual project. But you have that full-blown operating system. And in the case here, Raspberry Pis, it's variants of Linux, or you can load on your own versions of operating systems and use them for different things as you see fit. Like, say, examples like Raspberry Pis. Some people I know, like, you load them on where you get emulators to do old Nintendo games and stuff like that. And then you can hook it up, and then you can plug in other controllers. The idea of the Arduino is you could actually make your own, say, physical game controller and then connect it to a Raspberry Pi, and the Arduino controller, its microcontroller itself, handles all the sensors and the inputs of whatever way you make for your fancy kind of game controller, and then it connects to this microprocessor, which then would handle all of the actual game emulation, which is way more than an actual microcontroller could actually deal with, but they both communicate and have different tasks and come together, which is generally what you've had anyways when you're dealing with old Nintendo systems and controllers and everything of that fun. Now, within this family, there are other devices where then they will do a combination of both. And it's just because the market out there, people, what needs they have or market or what people want to start designing, that you'll get a combination sometimes of, yeah, you'll connect controllers and microprocessors together, or they'll design one controller board where it kind of tries to combine both together. That either it has an integrated microprocessor and controller on one board that are connected together for faster communication, or it's a hybrid of the two features, so between them. And this is an example of one called like the BeagleBone, which provides similar stuff that you would see for a controller like Arduino, and similar stuff to a microprocessor like the Raspberry Pis, but maybe a little bit more limited, because you can see a USB plug in here, you got power, you have network, but there's not stuff directly here for screens, unless like, oh no, see it down here at the bottom, HDMI, it's just using HDMI mini. It's got plugins for SD cards, but it's got things that look similar to everything else from there, and you can look deeper into this if you want. But you should know that you have these three kind of classifications of specialized boards that can connect to all, like, can connect to these combination boards, can connect to microprocessors, controllers. You have microcontrollers, being that one chip specialized program, or you have microprocessors and their power, or these kind of combinations of both. Now from here, you've got to start deciding, like, well, if I'm designing and I know that I need to have a controller and I need to worry about what features it has, maybe I can decide upon the specialized board later once I know what the main controller board is and what all works together. But I need to then decide, well, which one do I choose out of microprocessor and microcontroller? Now, in the beginning here, you could go with either. If you're working with basic projects like turning on an LED to flash, you can do it both. It's not a very big thing, but I prefer to work with microcontrollers in this case, because with a microprocessor, you almost have to set it up like a separate computer. You have to hook up your own monitor to it, some kind of keyboard to do your work, or you have to hook it up and connect it to your network and remotely connect to it. And if you've got that skills, that's fine, but not everyone that's coming to this course I know does, or is it really feasible to always keep doing that? Whereas the microcontrollers, you just need your own one computer, you plug it in, you have to install whatever software it needs to communicate to it, you need to do your computer programming, you need to compile it and transfer it to that device. But you also need to decide, like, well, what is your project? And like choosing which one is really more important, is about what works for your project. So I'm going to start with microcontrollers. Most people, if you've bought the kits, you probably stick with that. But if you're interested in other projects, then you can look into investing in, well, what do you need to buy and where can you get it from? And I can potentially help you, guide you towards some sources and areas that I've found. Now, hey, last time I didn't start the whole course with this whole lecture with a video, but I do have one now. Now, this video is older, and I mean at the point of me recording this, which is 2021. This video here is 8 years old. That does a comparison between a microcontroller and a microprocessor. And it talks about an example of an Arduino and a Raspberry Pi. And if you look at them, you'll see compared to the pictures I had before, they're also very rudimentary older boards. But what he says in the video is still very pertinent to give you an idea of, like, well, what do both provide and when is the best to use one over the other, and what combination of them do I start using? Oh, and this time, because it's been requested, I'll stroke my beard philosophically while I watch it.
There are a large number of controller boards that you can pick from for your projects. Two of the most popular are the Arduino and the Raspberry Pi. So, which one do you pick? On the surface, these boards look about the same. There are a couple of circuit boards with some chips and I/O connectors, right? In this episode of ARDUINO, we're going to take a look at the differences between these boards and how you choose one for your project. Let's start by looking at the Arduino. If we visit the product page on the Arduino website, you're going to see that there's many different boards available. So in this tutorial, we're going to focus on the Arduino Uno, which is based on the ATmega 328. Inside of the 328 is 2K of RAM, 32K of flash memory, some timers, and hardware that talks serial, I2C, and SPI, or also known as SPI. Outside of the chip, the Arduino board contains parts like voltage regulators, passive components, and the I/O connectors. It's a relatively simple design with an even simpler software structure. The code that you write in the IDE is the only code that runs on the chip. There's no interpreter, no operating system, and no firmware. Your C code is compiled into machine language, and then it runs on the Arduino itself. This is as bare bones as you can get. The Raspberry Pi, on the other hand, is actually a single board computer, or SBC. On the board, there's a 32-bit microprocessor and ports that support video, audio, USB host, Ethernet, SD cards, and even an HDMI port. There's also some GPIO headers that look like Arduino pins and are kind of like Arduino pins, but we'll talk about how they're different here in a little bit. Overall, what does this mean? Well, it means that your Raspberry Pi has more in common with your computer than it does in Arduino. For example, instead of writing code to control the hardware directly, you're actually writing programs that run within an operating system. In the case of the Raspberry Pi, the operating system is typically Linux. So I said the Arduino is a microcontroller and the Pi is a microprocessor. So then what's the difference between those two? They both have a CPU, which is what executes the instructions, timers, and memory, as well as I/O pins. But those I/O pins is where the key difference lies. Microcontrollers tend to have a strong I/O capability so that they can drive external hardware directly, while microprocessors tend to have weak I/O, which need transistors to drive most hardware. Microprocessors are good at processing, so they're a little bit brainier than a microcontroller. So for the sake of comparing the Arduino to the Pi, let's look at some raw specifications between the two. The Raspberry Pi has a clock speed that's over 40 times faster than the Arduino and is based on a 32-bit architecture. The Uno's RAM is measured in kilobytes, while the Pi's is measured in hundreds of megabytes. Both have general purpose I/O or GPIO, but the Arduino can drive or sync up to 40 milliamps, while the Pi is really limited to more around 5 milliamps. In terms of power consumption, the Pi consumes more power than the Arduino, but always keep in mind what is the project going to have and what other hardware is going to be included. Lastly, remember that the Pi usually runs some form of Linux, while the Arduino has no operating system. So at first, you might look at this and say, clearly, the Pi is better, but we have to really talk about how would you pick one of these for a project. It's not all about the specifications. This often leads to the question, which one is best, but there isn't a simple answer. It does get a little simpler when you add the phrase, for my project. Think about projects with things that get controlled, like motors, character LCDs, and sensors. These are going to work really well with a microcontroller like the Arduino. And then projects with things like video or cameras, complex math, and graphic interfaces are going to be better suited for the Raspberry Pi. Both boards have their place in the electronics world. Neither is perfect, and neither is going to be perfect for every single application. However, if your application is more about controlling things, the Arduino is probably a better choice, while if you need to process lots of data, the Pi is your best bet. For links and resources related to the Arduino and the Pi, as well as downloadable versions of this video.
Okay. So there you got a basic idea. So again, those were older boards, but you saw I said like that one of like the powerhouse for running I/O, so your input output being your actuators effectors. What size of memory it had, like the 2K versus 2 megabytes, that's a huge difference. So 2K being 1,000 bytes versus 2 megabytes being like 1,000,000 bytes you're working with. This is huge difference for what you can storage and do. When they said, you should have picked up on what it said for the power, for what it can actually run. That it said that it had like 40 milliamps versus 5 to 10 milliamps. And now remember, amps being, that's the measurement of current of what can flow, and enough current to be able to run stuff off of that. That 40 versus 5 to 10 is huge and different. So maybe the like the Raspberry Pi itself in that example would have to have more power sources. So that's just one example of generally talking about specifically the microcontrollers Arduino versus Raspberry Pi, but also talking in general like the different cases of why you would use a microcontroller over a microprocessor, and the fact that each microcontroller and processor is going to have its different capabilities, like power of what it can actually drive, how many connections it can actually have. Like that earlier version of the Raspberry Pi had very few I/O pins, which means limiting of how many things you can connect, whereas the Arduino had more, and different controllers have more. So it's really what is your project that you're working on. If you were going to do something vision analysis that you're writing from scratch yourself, maybe you're going to need a microprocessor instead. And you're dealing with camera stuff. Or you're dealing with a microcontroller and you write your code, but then you need a specialized board where that work is pre-done for you already, and then you connect to it and send commands, and then that other kind of image processing controller does the work for you. Depends upon what you're working with. Okay. Boom.
There are a lot.
So, as I mentioned before, and I'm just kind of repeating this, and hopefully we'll get to this in this course, but something that you can do as well is that when designing your project is that you can combine Arduinos and Raspberry Pis, or you can combine the microcontrollers and microprocessors through different ways that they're connected through. You can see some examples here of this being an older Raspberry Pi, and you get multiple different types of, these are all different types of Arduinos and devices here that, and let's say this one that I'm circling here is connected through USB, and there is a way to communicate from a controller through the USB cable to a microprocessor that it's actually connected to, so that they can send information back and forth from each other, and then you have different things connected on top of it from there. So the fun depends on the project, but we're going to start simpler and kind of build up from there. So we're coming along. We're about halfway through for this lecture. We need to add some extra terms to this now. So we're going through, we got the types of controllers, you need to worry about them. And now I'm going to get to more specifics and work our way down to more specifics about Arduino and the controllers that we're going to, microcontrollers that we're going to concentrate with in this course. So earlier, like I had mentioned, that controllers deal with power supply and points of where you can connect sensors, effectors, and actuators. And the general term or terminology you're going to get for this between microcontrollers and microprocessors is pins. And being a pin being it is a physical connection point, generally providing some way to allow for the connection of conductive material to other conductive material. So like your wires or anything else you're dealing with. So some pronged extrusion, or it's something like a breadboard kind of thing. It looks like it, that you have externally insulating plastic type material with some kind of slot, and in the slot is an exposed piece of actual metal that then you can make contact to with some other metal like a wire, and they're controlled from there. Like examples for the Raspberry Pi that you see here to the left, again, that you have these pins here. So each one, it's just a piece of conductive metal. So each individual single pin that you see there, but they are then connected in through other lines, connected material to other devices that are inside of the actual overall board itself. And then they allow you to connect things like the M slot kind of jumper cables that are used to, because you can see this is like, oh no, sorry, the F slot ones versus the kind of M prong type one. So this is kind of like an M prong. You go to an F slot kind of one that you will slot into these and connect, and then you make that kind of conductive jumper connection. But what you need to worry about is how do I connect those? And that's part of the microprocessor or microcontroller you're looking at, is whatever you get, you need to look at its specifications and where the pins are located physically and what do they provide. And this is going to be different for every board you actually deal with. So basic kind of layouts is kind of like the one that we see here to the left. So when you work with it, you have to look down to them. So the one to the left, I'll talk about more later on, is an Arduino Nano. It's a microcontroller itself. It has ways that you provide information to it. So this little chip you hear is square, diamondy shape. That's the actual microcontroller chip. You have some LEDs that are on the top here. You have things that tell you stuff like power and everything else. TX and RX I'll talk about later on. But what you'll get is, okay, well, once again, I have either prongs that are coming up, or I have little holes that you'll see that have an exposed piece of metal that you can what's called solder or put a wire in or connect to there, and at specific locations. And in this case, they're nicely labeled for you and give the conventions, but each one of these then is a different type of pin and a different way that you connect from it. And right now, a lot of this, unless you have previous experience, and a lot of you don't, which is perfectly fine, it's going to be all gobbledygook. Like, what are all of them? But there's little things you can probably pick up on, like, hey, look, like plus 5 volts. So volts is that measurement of that potential that's in storage for power storage. And so this is, well, positive 5 volts. So this probably means that that's your positive terminal. It's going to provide 5 volts of actual energy. So from this pin coming off of there. We should probably look for the analogous of, well, we need to know for a circuit that we need to have a negative pin, sometimes also referred to as ground or GND. And you can see we have a ground pin here, and you can see you got GND right there. So, hey, look, if I was trying to get power, I kind of know that, well, maybe this is giving me 5 volts, and this is ground. So these are kind of like the two terminals that we need for our circuit to complete that kind of overall circuit to get everything working. And we can share them and see if we have everything else. The rest of these, like, we'll be going through some of these, and they're similar to the Arduino, but you have to think, again, when you're looking at your controller, you need to look up specifications for what are the pins and how are they physically located. So even that Raspberry Pi you saw before is, well, generally you have to count or use some other kind of device that helps you make it easier, but you count down, like, okay, the third pin from the top is this thing, but you look that up in actual specification. Now, another term. Because you have pin that provides power and things that are specialty things for the controller board and connecting things to it, and you have things for your external connecting sensors and everything else. You will also get the terminology called GPIO pin, which just basically is an acronym for General Purpose Input-Output Pins, so GPIO. It's an uncommitted digital signal pin, being that it's not committed to one task like power or ground or something else. It is specifically that it can be used for input or output signals. So either it's something you've connected that's going to send a signal coming in, so on, off, whatever kind of thing, or it's going to send some kind of signal out. Depends what you're doing. And it generally, like, this is then done by you when you're doing the programming or you're setting stuff up in this course, is that you'll have GPIO pins. Some are specific for other things, and depending what they are, but they'll be marked as GPIO. Some have extra abilities on top, but then in the code, you'll specify, okay, this pin that's on the physical board, I'm going to use it for reading information in. So accepting that I will read for a signal that's coming in, or I will be sending out a signal. Kind of like a light switch, either like turning it on and off for sending, or receiving as you're watching to see, oh yes, on, off, like what's coming from there. So an example is, again, we go back to the Raspberry Pi being a microprocessor. We have the pins and they're numbered, and the idea is like, well, you know, how you orientate the board, you can kind of see it here from where the USB network plugins would be. You'd hold it up and then you get, okay, I can now line these up. That's pin 1, pin 2, pin 3, pin 4, pin 5, pin 6, and so forth down to pin 40. And then you can see, okay, the markers for what's what. So, oh, hey, look, this is 3.3 volt. Hey, look, there's 5 volt ground, so give it power. But then now a lot of it may still be gobbledygook, like what's PWM, what's all the rest of these, but you can see the acronym there, GPIO. So it means, okay, this pin right here, so pin 11, that counting in this order we have right here is called GPIO. So the general purpose input and output. This number that's next to it is basically the name that's associated with it that you have to get used to it. So, I'll be counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 coming down here, but internally within the hardware and everything else, it's referenced and talked about as being the general purpose input and output pin number 17. And so in your code, when you're wanting to indicate, okay, I want to use a pin 7, like the GPIO pin 17 a certain way, you're going to be use that number 17 importantly, and when you're doing work with it. But that's again for the Raspberry Pis. If we go with an Arduino Uno, you can see a similar thing for this kind of breakdown. And most of the Unos, and another reason why I'm using them, is they have it kind of labeled on it for easy to read. You don't need to count down. You're like, okay, well, right next to this little hole, I see these number and other kind of sequences and stuff that's telling me information. So here, instead, when you're working with the Arduinos, you will see that you kind of have this plastic insulator cores on the outside. They're kind of like the breadboards. You have these open slots, and internally they'll be metal, and you'll be plugging in the M kind of prong jumper cables or wires into this directly here for this Uno board, the way it's designed. And then you're looking for what you want to work for like, well, we got power, we got ground stuff, but then we have other pins that we're actually working with across the board. And some are specialized, and we'll get into like what the heck does analog and digital mean? What does this little tilde mean, and what does that make it special? But we know that we have the GPIO pin 10, and that's this one here, physically located here. So that if we're writing code and we're talking again about general purpose input output pin 10, we are talking about whatever the heck is connected or plugged in at that point in time. Just to keep getting pedantic about this, here's another example. This is a variation of like an Arduino microcontroller. It may be an Adafruit Feather. This one itself has extra things in here that you have, like the controller, other power stuff, but you have built in that it'll do Wi-Fi, everything for you. That ESP82 is kind of standard chip for dealing with stuff for power, and I don't know anything beyond that. Not power, I mean dealing with Wi-Fi, but it's built in. But the idea is that it will have prongs that like basically conductive points that you can connect other conductive material to, and each one is then labeled, and you say again you have the GPIO. So this is just trying to hammer home that point that you need to like worry about, okay, once I know the controller I'm working with and I've picked on it, what does it provide for these pins, which again, the number of them and how many give you limitations depending on what else you're connecting on, but you need to look up this specification and always keep this in mind when you're working with it. So, all coming down to the fact that we have all of these and things you could pick for your own projects if you're working on it, but for this course we need to start with one common one that we can work together on, and I have picked Arduino Uno microcontroller. And I want to spend a little bit of time justifying why I picked this as a starting point, and it really goes back to what I said at the beginning of, does it have community support for these devices and being out there for what you guys could find for information, what's easily accessible for free or paid courses, and even for connecting other devices and supplying stuff to this, and a whole marketplace and designers and builders from this, is you get really what's called Arduino. Arduino Uno is just a specific name of one type of microcontroller and specification, but there are a whole bunch of Arduino-based devices that are out there. So being that either they're direct models from the Arduino Foundation and company, or they're other companies that have made variations based upon what they provided and kind of made specialized ones or things for different uses, but they kind of provide this whole platform of a similar common language, a similar common like development tool to work with, and kind of common environment for how things connect and naming everything. So, and building up from there. Now, what is Arduino? Separate from microcontrollers, separate from everything else, is like Arduino is an open source electronics platform and foundation itself. based on easy to use hardware and software from their design. So boards are able to like read inputs, read and write inputs, deal with lights and sensors and basic things like that, and pushing information to each other from there. But the biggest part from here is that open source electronics. So it's not just open source software that's then shared open, it's also the design of the hardware is open, allowing other companies then to take that open design and either manufacture that design themselves and put their name on, or make slight variations to it, and they're not stealing any intellectual property because they're following those open source community guidelines for electronics and devices. And this opens up the market then for what I always keep like using the term Arduino based devices, that they're based upon this open source electronics and software platform, and then can be specialized and built off of there. And then there's this whole community of home hackers and industry and so forth that all combine this together. And you can go to the Arduino website there. So the like www.arduino.cc, this is the main foundation website where you can find tutorials, language references, and so forth from there to kind of expand. And use that as supplementary information to this course. If you want to keep going beyond that, you're finding that you know a lot of this and you want to go more, well, jump into that community and maybe become part of it or what they provide. So we'll get into this more of like dealing with the ID, like development environment and everything else and the language itself. And I'll try doing it more live examples, teaching you the syntax and semantics of what's needed as we add new things into it and what makes this different from coding that you've done before. And you have to keep that in mind, that you have to be a little bit open-minded, not so rigid to what you're used to for whatever programming language and things you've dealt with before, which was just a general purpose program, where these are now specialized programs working with specialized hardware. And so you have to think about what's differently that's going on, what's happening in my code that I'm writing, and then how is that specialized device specifically running my code or program at all. And it's a combination of being kind of aware of both digital software and external physical hardware at the same time while you're building a program and project, which is what you're doing with anything else related to more complex robotic projects anyways. So more of the rest of this says that like Arduino was born out of like a design institute as easy tools for fast prototyping, aimed at students and with a very little background electronics and programming that's actually required. So like that was their focus, and you get more specialized things that build upon it. And like again, it doesn't mean that like everything is as super easy. Maybe someone else developed a tool to make it easier, but there is a lot easier than the really low end stuff if you go even deeper into this. And it's also now reached a wider community of people who started designing their own boards, their own tools, IoT, so the Internet of Things applications, and in between that, even the Arduino website themselves allows some interface for wearable technology, 3D printing, embedded environments, and so forth. So it kind of expands beyond this. And so when they made their own boards, and you can even see in the picture to the left, this is just a picture now of a whole bunch of different Arduino-based devices, where you get some Unos, you get what's called Nanos here, which are basically the Uno, just a whole lot smaller in form factor, and you have other ones that come up as well, and I'll have some examples, but you can keep researching them. Now again, like the Arduino boards themselves are completely open source, so empowering users to build them independently themselves. So buy the components, buy the chip, which is called that ATM Omega, blah, blah, blah. That is the actual general chip, the microchip that the Arduinos are based upon, or you get variations of it, and making your own new growth. Like the one to the left is the one that we're currently using in 2021, is the kit that I've suggested people to use, which is from Freenova. And generally it's because it was cheaper. Instead of spending hundreds of dollars, I was like, here's a kit that's like $40 Canadian, and provides basic access to one Arduino, like Arduino Uno based kind of controller, that same specification, which includes the size of it and the location of everything. So things are also physically compatible in between different manufacturers if you say that you're producing an Uno. From there. And so like you'll see variations of like the chip itself here is a little bit smaller and so forth, but everything else will work the same. Now coming back to like the Arduino based controllers is again, the different manufacturers and type of ones that you'll actually get. And so there may be different reasons why you get to this, like what they have for plugins, like adapters on top. The one I'm circling here, and you'll see again in the future, is an Arduino Mega, which is just like the Uno. It just provides a whole lot more of actual connectors. So it expands upon the power that can be provided. It also expands upon the number of digital and analog and your GPIO pins and power pins. And so it means that off of one controller, if you have a whole bunch of sensors, maybe you don't need as many external boards, or you can connect more things versus you're more limited by the Uno, but depends what the project you're working on. Or this earlier version's probably replaced by now of the Arduino Yun, which is an amalgamation of trying to get and basically the form factor of an Uno, but provides some power and connection of being a microprocessor built in and other information like that. It's all these specifications, and I say again, like, woo, woo, woo. Look at everything else around me. Again, more of all of these other types of boards, and that's what I mean. Like when you're picking it, you'll start with it, but you look at manufacturers and stuff you need, and what's the community around them, and all of these ones are all Arduino based. You get ones that are easy to spot. The size, there's Unos from right here, like I don't like all the zero, but that looks like an Uno. From here is a Yun. You have a Mega. You have other peripheral boards that do extra things. You have an example of a specialized controller board here. This looks like it's a RFID or Bluetooth or whatnot. It's probably an RFID one. I'm only looking just because I can see this metal bit here that looks like an antenna. You also have what these I can identify that look like Adafruit feathers, which are also Arduino based, that provide other connectors. But there's a lot of commonality. Like it gets confusing in the very beginning to know what to start with. But the point is that you can get some commonality. You look stuff up, you go work with tutorials, and you keep expanding and growing as you go. And you see, well, what do they provide for environments for what I can work with? Again, like going more specialist pictures, you can see them closer here, is comparing three factors of just like different types of Arduino-based devices of the Uno that we'll be using. You have the Mega, and you can see, well, they kind of look the same. They kind of have the same barrel jack adapters. They have here where you're plugging in to download computer, like connect USB to your computer. You have all of these kind of like outside pins where you can connect to stuff. But the Mega has way more of them. You can see numbered 42, there's way less here. And this is usually larger. The Mega will be like double the size of the actual Uno, so it will take up more space. Versus something like this, which is a Nano, which basically is exactly the same as the Uno. It's same power, same number of connectors and everything like that, but the form factor is a lot smaller, and this is zoomed up. The Uno will be about that big, the Nano will be about the size of a stick of gum, and you can see instead of having these prongs protruding, that you have the little holes with exposed metal that you can then solder. So like sometimes what I'll do is like I'll prototype with an Uno, and then when it comes to building the physical device, I will then use a Nano itself and build it right into the actual project. It's a lot smaller and takes up a whole lot less space for what you're working on. So just depends upon what you're going with, and sometimes you can get these like dirt cheap for $5 to $1, depending on where you're buying it from. Versus other things like this being Adafruit. Adafruit is a company that you can look up that does a lot of stuff from right now with Arduinos and has their own devices, but these are called feathers. So feather being like they're thinner, and more narrower, and there's a whole family of things that they provide, but we still have things like these pins. You have things that allow for like Bluetooth other connections. You have connections here so you can hook up lithium polymer batteries and have other power sources directly, and that usually these boards like the feathers are designed that they'll also charge those batteries for you. So if you want to have something that doesn't run off batteries and is rechargeable and you don't want to buy external boards to deal with that, they have them in here. The world grows. Or you get designed ones that are designed more for wearable technology, being that they're flat, they provide these open prongs, and they're still numbered. They have their own controller, maybe some built-in sensors, and in some cases, like these ones here, you have stitching thread, which is conductive thread, so it means it has conductive material in that thread, which is then making connections and acting as your wires, so that you can put this into physical clothing or other wearable devices, depending upon what you're doing. So it's the fun of experimenting. That's why we're just sticking with the Uno to start to learn with. But the idea is that building blocks that you're like, okay, I can go to the next device that's very similar, and I can probably take a lot of my same skills and just learn what's the difference between the two and what new advantages does it actually provide. Okay. more terminology that I just want to throw in for now and we mention later on is that with Arduinos themselves and the family of it, you'll get this thing that's called a shield. So what these are is designed is they wanted to make it so that some things were stackable. So you will have specialized controllers and other boards you'll connect externally, which you can do, but they've also designed it so that you can have what's called these stackable shields, and this is where the size of the Uno comes into this. And so with these shields basically plug in and add extra features. They'll take up pins, they'll have specific requirements and power, but maybe they'll provide the fact that, well, the basic Uno has no networking or wireless at all, so maybe you need that, and so you plug them in. And the idea is you can keep stacking these up on top of each other to a certain point and add extra features. Like the one that's here shows an Uno on the bottom. This middle one here is allowing to have an SD cards plugged in for extra like storage of access to things. And then the top one that's supposed to be plugged in here is for networking. And you can see how they have the slots that are here. They have the pins that slide in, and a lot of times they'll do what's called pass-through. So even though all the pins are blocked below on the original Arduino, you can plug it into the top shield and then hopefully make it down to the bottom. But like everything, it has its own specifications as well, and you need to look into that. This other example here is for a feather, and this is one where they've designed it. It's just, instead of being like the same shield we're stacking, they've got them next to each other to make it easier to connect. Or you have one right here with an A-fruit feather that's under here, and what you have stacked on top of it is a shield for doing motor controllers. So once again, you have your separate controller. They just kind of make them where they stick together, and it's just depending upon what you're trying to fit into everything, what you have for power sources. So you can see like toy motor here, it's called a stepper motor, and this connector is right here, so you can disconnect and connect to other power sources to run said things. Yeah, but I've been talking fast, so I should like take a sip and slow down. So, and I just want to reiterate at this point in time that even though we got the shields, I just want you to know the terms that are there. We'll come back to it. You don't need to memorize it perfectly. I prefer to show that I can present it to people. You know it's aware of it as your first interaction with it. Then I'll bring it up again later on. But even though these were designed, it's from the Arduino Foundation, and this is more specific to this, it's not just to all microcontrollers, it's just like Arduinos, you get that term of shields, is that these external boards, you don't always have to use shields to do that. You could also just still design to have an external something connected to it. Like the example in the picture to the left is a separate board that you have a old Sega Genesis controller, and the idea that's in there is that that's just a microcontroller that's inside this darn thing. What you're plugging in here then is this through the insulated material in which you're holding it, so your hands aren't conducting stuff again if you connect to it. But there's this external board that, well, it plugs into as the connector that would be used normally for Sega Genesis being plugged in, but then it takes what's called each individual wire that's in that cable and pins them out. So you're right here, so that then those can then be connected, and that information can be used to be read from, or information sent back and forth between the two, which is an interesting thing that, well, you could now use an Arduino to modify and kind of like hack old controllers to do things for yourself, so that you could use the Sega Genesis as inputs to control something else in your robot or circuitry, or even in some cases, because this could be controlled to like connect to the computer, is as a way to use that Sega Genesis to control something on your computer. Depends what you want, but you can see all the jumper cables, you can see them taking up spots, but you can see that they're taking up a bunch, so this one thing takes a bunch, and we're limited after that. So things to keep in mind, and oh look, a breadboard in the background. So this is all this kind of fun thing. Just checking one thing. Okay, with the Unos, at the rest is that they then get more specifics. And so, like, there's going to be a lot of numbers and terms and stuff that are on these slides. And I'm not going to go super deep into it. Again, I just like presenting the basic information. And the fact that I said that when you're starting with a controller, you have to know its limitations and what it provides. And so we need to know about the pins and everything else that it provides. And so again, you don't need to memorize these yet or have to worry about this, understanding every aspect of it. You should just be aware it's first there, let it wash over you, and some of it stick to you for knowledge, and then know that you can come back here, know that for other devices you need to go into more specific. So it's open source, it's based upon one type of controller, which is one specific chip, and like there'll be variations in the future. The board itself generally has 14 digital GPIO pins. So this just means that, like, we'll get into what digital and analog means, what the difference here, but we have 14 that are specialized, that they're general purpose input output that we can work with. This PWM, don't worry about this yet. We'll get into that kind of in future lectures. And the same thing here when it comes to what it means analog pins. And so these are limitations, so that we know that we only have 14 of these and 6 of these. And so depending upon what we're hooking up, if one sensor or actuator effector requires a certain number of pins, those pins are taken, and we can't generally hook up 2 things to that one pin unless this is power. It's one thing plugged to one pin, that's it. And so that's part of the limitations. And you have the Arduino IDE for development, and we'll get into that and probably see more examples when you come to the physical videos, not as much for the simulator because it has its own kind of separate tool that you use for that, but similar language. And you have a USB cable which can be used to power and transfer programs to it, but you also have other ways that you can provide power to it. So not just through USB, that is just used for power and data. There's ways to power it from 9 volts, other power sources, and so forth from there. There's multiple different power ways you can power it, and you just have to look that up. Now, when it comes for how fast you execute instructions, and so the gamers in here will know all of this kind of stuff and how important that is in general, and like how fast can it do work. And it's just kind of like how fast can you execute an individual action. So an Arduino itself generally has a performance around 20 MIPS. So this means like 20 megahertz. And what the heck does that actually mean? It's like the megahertz means like how many millions of instructions per second, roughly, or time clock tick that the device can execute. And things you're never generally aware about, but there's millions to billions of instructions per second being executed on a general computer. It's being dealt with. But for here, you're like, no, it means every second it can only do like 20 million instructions per second. Versus when you hear the term gigahertz, so if you have a like 2.3 gigahertz CPU, and it's only one of them, like 1 gigahertz equals 1000 megahertz. And if you're 2.1, again, that's like 2.1 thousand megahertz, versus this is 20. But that's the point that microprocessors that would have these higher kind of rates for instructions can do a lot more work faster, but they can't handle the power horse of the input-output that the controllers can actually do. So you can still do a lot on these chips. You can do it to your level, and is doing it really freaking fast because you don't have this overhead of everything else that the operating system is taking up, but it's still not going to be the overall, like, you're not playing games on an Arduino. That's just not happening. And that's not the point of the device anyways. When it comes to things like memory as well, a lot smaller than you think, just on the built-in board. So built right into that chip, again, that's all on this chip. You have flash memory, so think of this like USB, whatever. Like basically this is where your program, the one program that could be in a microcontroller, is stored. And you have 32 kilobytes. So remember, megabytes is meaning millions of bytes of storage, and kilo meaning thousands. So this means you have 32,000 bytes of rough storage, which is smaller. Megabytes way, way larger. You're thinking millions versus thousands. When it says here SRAM, RAM, this is where, like, so the flash memory is where your program's stored. So at most, when your program is compiled, so from your text version that you're working on the computer, and it's converted into the binary version that the actual device needs, they're using that controller, the compiler to convert it, is that at most the program can be 32 kilobytes in size. So you're limited. When it's running, you only have for your variables, so this is all your variables and everything else, your data structures that you're storing on it, you only have 2 kilobytes of storage. And this is what I mean, that you can't just make an array that's massively large. And you have to worry about, well, if I'm storing information, I have to remember on physical hardware that data, like an integer like 1, or saying something is an integer, takes up a specific amount of memory, like a specific size of a file. So we need to worry about that as well. The Arduinos also provide what's called the EEPROM memory. This is non-volatile. So like, it means that where you can save stuff. Because like the flash memory where your program is, you lose power, that program's still there. Your program shuts down or your device loses power, anything that's in the RAM is wiped away. That's gone. So your program, while it's running, your variables and all that data, the machine shuts down, you start it back up, those variables are blank and just the whole program starting from new. So it's like shutting down your program and then running it again. The EEPROM is kind of like having a program and you're saving stuff to file and coming back. It's a very loose analogy when it comes to this. But this means that there's a very small region of memory that you can put stuff into and retrieve it, but then if you lose power, it's still there. So let's say your device, you want to have settings that you're keeping so that when the device is turned off and comes back on and you want to have it the same settings you had before, you can read and write to that location. But you only have 1 kilobyte. So 1,000 bytes of actual storage. So here again, it's limited, and how you access and work with it's differently. And my hopes is later in the course to have a demo of this as well. So all this kind of stuff that you're like, probably like, wow, what's the point? The point is knowing that this is the UNO. I said from the beginning, when you're getting to your controllers, you have to know the limitations and specifications of what you're working with. And this is one thing. Now, everything that we're building on this for like the basic stuff we're starting with of the RAM and flash memory is not going to be an issue. But for future things, you have to worry about that. Now, other things that you're worrying about, and I'm not going through all of these, is then to understand, I said again, that pin kind of breakdown. And you're used to things like your GPIO is digital, you have other connectors, you have a whole range of area for power that you're getting, the 3.3 volt versus 5, which is some sensors need a different amount. You have ground, you have things like VN, which you don't need to worry about this, but being what's called voltage in, a different way to power it. You have a barrel power jack that you can then use to power it separately. So if you want to hook it to a 9-volt battery or some other kind of power source, you can do that. You have a USB that'll connect to another computer that you'll generally plug in to here, plug it into your laptop or computer, and then you'll generally use that to compile your program and transfer the program you've written from your computer onto the actual chip itself. Or use the power that USBs do provide, which is 5 volts, I think around 1 amp or so, to run the actual overall device itself. So when we're starting this, it'll generally be the USB port here that we're using for power to run everything. But in the future, if you're putting this into some other device, you can use these cases. And like, I'll show examples in the future of all of it. And so you don't need to understand everything perfectly here. As we work with the device, I'll be going through more and more of these actual examples. Now here I just wanted to have like a close-up just to say again that like for this semester in 2021, we have the FreeNova, and being it's open source, that it may look slightly different, but the fact the form factor is that the shape and size and layout of where the pins are and everything will be the same. So where these even holes for connecting stuff are, if you're screwing into boards, buttons, your power, everything else, and this kind of stuff, is all the same physical size. That's part of that open source design. It's just how they change it, and that they have a different chip that they're running stuff off of, but the way that you program it will be the same and work with it is effectively the same. You just get like a micro C kind of connector. It's much smaller than the older devices, because those are devices from years ago to now, and it's cheaper, but just different ways, but it's the same kind of idea. So you don't have to worry about which version you have of the actual device itself. Whew, a lot more coming closer. Only about 10 more slides to go before you go off and watch the next videos. So here, as I said, the Arduino Uno is a platform, not just being this device, not Arduino, but the Arduino is a platform that's providing a language, a development environment, and these range of different boards and stuff you can work with, and is that open source. And so when you have your development environment, your IDE, they made a very basic one, and it's based upon, like if you've ever worked with processing, which some people may or may not have, it's another development language that's very visual, is that the environment is a lot simpler. It's not this high-end crazy IDE like Eclipse, or if people have dealt with that for Java, or IPython, or other stuff like that, whatever editors and things that you're actually using. It's just a lot more simplistic one, which is the point of the market, who they're targeting for. You can probably find other IDEs that people develop that do a lot more complex things, or plugins to ones you want for the course, but the general purpose one that we're using here, just to keep it simpler to start with, is you just have your files that you're working on. You can see your code. You have your output from compiling and error messages, and you have your control kind of buttons for what you're doing for compiling or uploading on there. And you have your own language, and let know that this is it's a variant of C. and some stuff from there. It's not exactly like it, but so again, it's not Java, it's not Python that we're going to be working with here, and it's not exactly C or C++, but there's a lot of commonality between it. So again, please don't just make presumptions about what you're writing and be a little bit careful. Things like adding semicolons or not. People who've done Python, you're not going to have to do the tabbing to indent. You're going to have to learn how you add curly braces and that kind of differences. And I don't expect everyone to be perfect at this at the beginning. And the idea is that as I introduce stuff, I'll also be talking about the language itself. So when I go into the simulator video and the physical video, I'll be doing demos of the language. And I'll still ask you, please, you watch both videos, not just the simulator. Please watch also the physical. I'm trying to introduce new things in each of them and stuff that you should get used to. Now, when working with the board, I'm going to go through some basic steps of this, and I'll demo it again and again and again. And I just want to get a general process of like, how are you doing your work with it? And one, always remembering that you are working with power and electronic devices, and so you want to be careful with what you're doing with the power. We are right now working with lower power stuff, but if you're working with more intense motors, you got to be more careful. And so you should generally deal with one of first making sure you have nothing connected, no power to the actual system. So unplug the Arduino or anything else, your power sources from it. You then want to connect or change any of your wiring. So using a wiring or schematic diagram or your breadboards, your jumpers and whatnot, you're connecting in between this, building your circuits, connecting it specifically to the Arduino as your controller as you see fit, doing all of that work. You'll then have the IDE from here. So for programming, again, doing the rest of your work, you have your IDE. If it's the first time you're connecting this, you're going to have some specific ways to set this up with the Arduino IDE. Like the simulator, you don't need to do this because it's a simulator. But when it comes to physically, you need to set up a few things of like, well, this is a development environment that allows for multiple different Arduino-based boards. So for the first time you're doing it, you need to select what's your type of board so it knows how to convert the language to what's specifically required for that board. Most times this by default will be here. You can see tools and then board, and I'll demo this under the physical kind of things. You do your coding, you do your rest of your work. You also need to generally convert what's called the port because you're connecting the device through USB, and so you have to make sure that you know what board you're compiling it to, and the fact that when you're compiling, you're not compiling for the run on the computer that you're on right now. You're compiling so you load the program onto the microcontroller, which is separately to do your work. So your code, you compile, and it transfers it over through the USB cable that you have connected to, and these are called these serial ports, which will be named differently if you're on Linux, Windows, or Mac, but you'll see demos of it, or you get the idea. And you'll see that they're named, and it's not too hard to know like which one you're picking. It'll have, like, if you're working with an Uno board, you'll see an Uno next to it. I will point out, though, sometime when you're working with physical boards, sometimes if something is not connecting or something's wrong, you need to come back and check this serial port to make sure that something hasn't changed from the rest of it. So fun. The next steps from here is do all your programming, whatever you want. Open up an example, open up what's called a sketch. Sketch is the name for like one program you're working with for Arduino, just their own terminology. You connect the actual Arduino itself to it, and then you'll do things like, oh, I'll hit the buttons for uploading, which will compile it, give you any errors. If it's completely right, it'll then transfer it over to the actual device, and you'll get flashing lights and indicators that this is actually happening, because you'll have your computer, say like the one I'm on right now, recording this video, connected to the actual Arduino and doing that work. And so in the simulator, you won't see this, but in the physical video, you will. So again, watch those because I will have questions and stuff about that for you in the future. And so when you're uploading it, one thing you want to first look for, and I'll demo it, is you have little tiny LEDs that are on here. That's this L, and you have this TX, TR, and there's also TX, TR you'll see here. TX is generally referring to transmission, and RX means receiving. And so when the TX light is flashing, that means that information is being transferred from the Arduino to whatever is connected to it, and it flashes at different rates depending on the speed, and RX means when it's receiving. So for you right now, this really means that when you're when it's disconnected and it's transferring information over and the Arduino's confirming that it got the information, you're going to see these two little lights on the board flash a whole ton, and you'll see that in the live demo. For more tutorials and stuff, if you want to, in libraries and everything else to go beyond this, and also just as your reference to look up the syntax and other things that you can do in the language, these are some direct links that when you download the PowerPoints or the PDF, you can go to the Arduino website. Basically, you can see these are like Arduino website and then tutorial point, and this is all your reference for the language, which is very good to know. Have that in your back pocket. Open this while you're doing the rest of your actual work. Whew. Okay, another sip. Take a little bit break. As we're an hour and a half in, there's only about 7 more slides. There's a lot of information on these next ones. But again, please don't feel like you have to understand everything that's going on perfect here. I don't try to just present information once. I'll come back to this. This is just to give you a general idea, and I'll talk about it again in the other videos for the simulator and the physical work, and in future lectures. Every time we go over stuff, I'll reiterate it. And I just want to give you a general beginning point of how things work differently. And so in the simulators and physical work, you'll get a more in-depth relation to this, and you'll see it more and more reiterated for future lectures. But when you're looking at any example programs in the very beginning, and you can see different syntax and everything here, generally you still have comments and things like your introduction for the program. You get your variable declaration, which is called global, and these are kind of differently. These are like what it means to declaring a variable here versus inside. You got functions and everything else. But then you have special things like what's called your setup function and your loop function, and then the stuff that happens within them. And they're very important because every program will have what's called your global variables that are always accessible. You'll have local variables as well. You will always have a setup function, and you'll always have a void loop function right here. So you can see between the brackets. So the people in Python who don't know those yet, the opening and closing brackets here is the equivalent to indentation. You don't have anything else to say this is inside. So like this is your function. This is what it will be done, and then when it's called. Now, why these are always here is that you'll never see these directly called yourself, but in the hardware itself, remember that the controllers only run one program. When it's converted over and your controller starts up, it knows where those functions are and it calls it. So the processor on the microcontroller actually will call these functions. And you can guess kind of how these work, but we'll come to them a lot. This is a very quick introduction, so this has already been an hour and a half lecture. We'll go through this again and again. But to get a basic idea of what happens is you have these global variables where you store stuff that you'll be retrieving and doing work with. You have a setup function, which is initialization, so that when the controller starts, this function is called first, which is to set everything up. Like setting up memory, initializing variables, determining and stating what your GPIO pins that you're using will be used for, and initializing of any data structures or things that you're working with. Once the setup function is done doing its work, then the loop function is called after that. And what happens is, like, this is kind of like your main when you're working for any other program. This is where it starts running, but you can't think of it like before, like these ones here, where you go to the bottom, you hit the bottom here, and the program shuts down, and that's it. Why they call this loop is that basically it goes to the first instruction, goes to the end of the loop function, and then goes back up to the top and just automatically runs it and does that infinitely until the controller has lost power or told to shut down. So right here, you have these 1, 2, 3, 4 lines of code. They're calling 4 built-in functions. The idea is that this is going to execute, go down to the bottom, come back up, and just keep running again and again and again and again and again and again. And this sounds weird, but it's going to be important to get into your head to not think of this like a main where you try to do everything, like robot do this, then this, then this, and by the end the program shuts down. It's like, well, no, you want to take advantage of it, that it's constantly doing this kind of controlled loop, robot control loop cycle, sense, think, act, kind of work, and taking advantage of that to get your controlled closed loop kind of control. So there's lots of stuff from right here, and there's basic things that, like, I don't want to go through everything, detailing, boring you with a monotone voice of, like, what every function is that I plan to, when we're doing more live coding and kind of live show some of the language bits as you need to, and that these slides can work as your first reference of important stuff that you'll see. Things like your declaration of variables that you see here. of initializing it, the semicolon. People who've done C and Java will get used to this. People who've done Python, you'll have to note things like this semicolon is different. This is the marker instead where you normally hit enter, and go to a new line. This semicolon marks the end of a line. Normally for Python, you just be going some name equals and then putting a value, and that makes a variable for you. Here instead in the Arduino land in the C and Java, you have to say, well, it's not just a variable. What is the memory type of that variable? So is it integers being just 13, 14, 15? Is it floating point or doubles being like 13.1 or 13.2 and so forth from there? So if you're coming from the science courses or more of just only Python coming into this course, the first thing you should be doing is looking into more tutorials about these memory and these type and what it is there. And if you need extra help, please just reach out to me and we'll set up meetings to go over that and give you specialized help into going from Python to like this Arduino based kind of programming. But again, I'll have slow examples as we go. Setup function in there, you'll see calls to other built-in functions like pin mode and serial.begin. Pin mode is just an example, one that says this GPIO pin is going to be for input, or this GPIO pin is going to be for output, and variations from there. Loop function, you'll see a whole ton of them from right here, but the idea is like, really what all these are is doing work for you, but if you're trying to either send information to a pin or get information from an actual pin, you use a function, like digital write, digital read, analog write, delay, slowing stuff down, and so forth from there. And we'll all have live examples, but you don't need to worry about too much about that yet. Just get used to this fact of this looping part of this, because that's what's the most important as we keep going on here, is why I tried to introduce the idea of that robot control loop earlier on, and that you're going from sense, think, act. And the idea is that you can't think of this like your usual programs you've been writing of like, ask input from user, do some work, send out output to user, or have a loop that sits there doing some actions forever. Instead, you've kind of always got to be doing that. Your robot is, well, this is the controller of the brain. It's in a physical environment with sensors, effectors, actuators on, and things are happening around in that environment at a fast pace. So you're generally reading sensors, doing some quick thinking and changing of variables, your states, and doing some quick action based upon the state or what you're in, and then going back to the sense. Not like think, but then you're never getting sensors and you're never doing any action and your robot crashed into a wall. You're like, have I reached the point yet? Have I reached the point yet? Have I reached the point yet? Yes, I've reached the point yet. Slow down, turn right, turn left. Like you're going through these little actions. And future lectures as we keep building up, because this is now just like roughly the third week or whatever we're into this now, we'll go into more and more examples as we build up from this and kind of give you more context to what I'm talking about. This is just that first layer and we'll keep digging deeper. So please don't feel overwhelmed at this point. Just kind of get a general feel, know that you've seen this here, and then we'll come back to it again. And finally, the last slide before I go on to the simulator and the physical videos. So, like, the next step is I'll be demoing how to use the Arduino in the simulator that we're using this semester and start learning some of the basics of how to program it. So we're going with very, very basics. I don't want to go too far with this yet. It's already enough for this week for what you have to deal with. And then following from there, I'll deal with demoing, installing everything you need to deal with for the Arduinos themselves. So I'm going to go from I don't have anything, and so downloading the actual IDE, installing it, connecting the actual Arduino, and then doing some work with it, and then physically showing the steps of changing the code and uploading it to the device. So please watch both of these. Even if you're not working with the physical devices and you're just doing the simulator, please watch both. Things like there's more that you learn between the two of these. And like if you've skipped the previous physical or simulator videos, please go back and watch those. There's a lot that both teach you, and there's some things in simulators that you don't experience that you get in the physical environment and get in the full course of what you can learn in this course itself. So from there, I'm sitting at about an hour and 38 minutes, and so I'll stop this video, and like I've started to make a new habit now. I just want to step back even from this course and everything else and remind you, like, please check in on yourself. Like, how crazy are you in your courses and everything else? Have you taken time to take care of yourself? Have you reached out to others to see how they're doing, even if it's just teachers? Like, see how they're doing. We're people too. To your friends or someone you haven't heard from in a while, and make sure that they're okay. Um, like taking care of yourself can also be a way to take care of other people, because if you check in and make sure yourself, you're better prepared to help other people at that point in time, or other people don't have to worry so much and so forth, and you can deal with things. And I'll probably say at the end of this video, like, why do I keep doing this? Because I just like compassion and caring about people. And I'm also tired of dealing with the fact of how many friends that I know are now dead, that have committed suicide. And like, I feel bad that I didn't reach out to them. And I know I can't fix everything, but like, that's an extreme case. But maybe just knowing that you care and you care about them can make a difference. And it's part of why I do this, and just trying to every day try to be a better person. Where none of us are perfect, no matter how much you may think you are. But like, we can always improve and be better and take better, proper, selfish care of ourselves and important of ourselves. And also remember that we're connected to a community of people, and we can try to help people around us in some way. After that rant of 2 minutes, thank you for listening at this point. Please go on and continue being the fantastic students and people that I know you to be, and have a great day. And watch the simulator and physical work videos.